Okay, so we've been saying that the geostrophic flow doesn't vary in the direction of the rotational vector, and barotropic fluid doesn't vary parallel to the direction of rotation at all, right? So we started with our geostrophic flow, UG, VG, and then we assume for rho and F being constant, we said we can easily derive dUg dz, dVg dz to be 0 because we can replace dP dz with rho g with our geostrophic, and then we see that it cannot have a y derivative, and similarly it cannot have a x derivative. So dVg dz and dUg dz have to be 0. So geostrophic flow doesn't vary in the z direction. The more general expression of this was by starting with our steady frictionless fluid, where we had assumed rho is just a function of pressure, so it's a barotropic fluid, and we derived the baroclinic vector, and we said in the case of barotropic fluid rho surfaces and p surfaces are parallel to each other, so grad rho cross grad p goes to 0. So we ended up with this expression 2 omega dot grad u equals the baroclinic vector, and we took the curl of this equation for the barotropic fluid and came up with the Taylor-Proudman theorem that omega dot u has to be 0. Omega dot is obvious that grad is obviously in the z direction, right? Omega is, in our case, we're not on the sphere, we're still in the setup where omega is in the z direction, right? So this reduces to du dz equals 0. U is the vector, and we said that's our Taylor-Proudman theorem. Why am I going through this again? Just to make sure that we are on the same page. Geostrophic flow for homogeneous fluid with rho constant and F constant. Geostrophic flow doesn't vary in the direction parallel to the rotation vector, whereas more generally speaking, barotropic fluid in a slow, steady, frictionless flow, the entire u, including the vertical velocity, cannot vary in the direction of rotation vector omega. Just to re-emphasize the concept, barotropic conditions this is now in the ocean, but obviously atmosphere is much more compressible, so it's more difficult. Nonetheless, in the ocean it's easy to show when you have isobaric and isopycnic constant density surfaces parallel to each other, you have barotropic conditions, and when they are not parallel to each other, we have baroclinic conditions. So baroclinicity is baroclinicity is essentially the deviation of the isopycnic and isobaric surfaces from each other. Okay, so what do we want to do? We say the large scale atmosphere is, we keep saying atmosphere, but the same for the ocean. Large scale balances are geostrophic and hydrostatic, right? Then why doesn't the atmosphere follow Taylor-Proudman theorem? Okay, why do we have zonal velocity varying in the vertical, local vertical, parallel to the local rotational vector? What happened to the good old Taylor-Proudman theorem in this case? Obviously, the atmosphere is not so barotropic, neither is the ocean really barotropic, but there are special cases where we do get Taylor columns in the ocean, Okay, we'll see an example. So this is another way to look at it. We'll come to explaining this vertical shear in terms of what we had already seen. In the barotropic atmosphere, all the constant pressure surfaces would be parallel to each other, and geostrophic wind would be constant in the vertical parallel to the axis of rotation. Okay, but since the atmosphere is baroclinic, we have the pressure surfaces increasing in slope with altitude. Why? Because remember that the tropics are warm and the tropopause is at 12 to 15 kilometers, and the tropopause drops off to about 8 kilometers into the higher latitudes towards the poles. So the temperature and pressure surfaces are not only sloping, but the slope increases with altitude, which means our geostrophic wind will also increase with altitude, which is what we are seeing here, right? So we have to modify our Taylor-Proudman and look for solutions that account for this baroclinicity, the fact that the pressure surfaces and density surfaces are not parallel to each other anymore, because there is a temperature dependence of density, as we know. P equals rho RT, so rho is dependent on P and T, right? So we're not deviating too far. We just, if we include the effects of large-scale balances for this density that's temperature dependent, then we will recover a solution that is still valid with the geostrophic and hydrostatic balances. Okay, this is just a good example from this paper here that looks at the Southern Ocean, and it's measuring currents. These are meridional currents, so meters per second. You can see ocean currents are much weaker than the winds in the atmosphere. And even though the ocean here has a topography, there is little seamounts in the middle, but the measured velocities with a so-called ADCP, or acoustic Doppler current profiler, which is basically sending acoustic signal and measuring the reflection which corresponds to the movement of the water. It tells you that there is a Taylor column like structure in the ocean in many places, and that works despite the seamounts, because the ocean is stratified just like the atmosphere. So the layers that don't feel the bottom topography can still have Taylor columns within them. We'll look at this again later on, but I just wanted to introduce you to the concept with the data. So the flow will go around the mound in that sense, but here in the lab experiment, remember the hockey puck we put in the bottom acts as if it's extending to the surface because you had homogeneous fluid, whereas here obviously the fluid has density changes because of temperature and salinity, but nonetheless the layers that are not feeling the bottom can still go through Taylor-Proudman theorem and create Taylor columns. Okay, that is really cute, and we will look at this a little bit more later on. So that should kind of make sure that you understood the Taylor-Proudman theorem and Taylor column properly without getting lost in the equations. Even the equations are fairly straightforward. We're just carrying geostrophic balance, hydrostatic balance. We added a barotropic fluid with rho as a function of pressure, or we had rho as constant, and we didn't worry about changes in F. We assumed F is constant, and so on. All these are very valid assumptions for large-scale circulations in specific contexts. So we are all good on our assumptions and the solutions we are showing.